Greetings and welcome to Mr. Van Lowe's poorly monetized low-budget science channel. Do not click like, do not subscribe. Okay, today we're going to look at topic 5.1. This is the second lesson. You have probably already watched the first video if you are here. If not, you may be interested in checking it out. We're going to talk about electric field current and potential difference. Not that. And our learning objectives are as follows. By the end of this lesson, you will be able to calculate work done in an electric field in both joules and electron volts. Identify sign and nature of charge carriers in a metal. Spoiler alert, they are electrons and negative. Next, identify drift speed of a charge carrier. Solve problems using the drift speed equation, and solve problems involving current, potential difference, and charge. So there you go. All right, so let's talk about electric fields. The space around a charged object is occupied by an invisible field, which we call an electric field. So any charged object has one of these fields. We define the electric field by placing a positive point charge near the object, the charged object, and then we determine the force exerted on that point charge. We want our charge to be as small as possible so that it does not distort the electric field. Okay, so if you have a charged object and you're attempting to measure its electric field with an equally charged object, you've got a problem. However, if your test charge is very, very small proportionately, then it's going to be a tiny fraction of your other charged object. Ideally, we would be using a proton as our test charge because that is the smallest possible positive charge. So let's talk about some conventions. If you have a positively charged object, as we do here, then our electric field arrows will point away from that positively charged object. If we add arrows, that indicates that our electric field strength is stronger. Okay, so this is a convention. We don't know how much stronger. We don't know the magnitude of this electric field versus this electric field. We just know that this object has a larger charge, and that's why its electric field is stronger. Okay, so here we have a negatively charged object, and you will notice that the electric field arrows point toward the negatively charged object. Okay, so if you look at Coulomb's law, where force is equal to Coulomb's constant times the product of the charges divided by distance squared, you should be able to explain why we have the direction of these arrows. Okay, and again, there's Coulomb's law. I will pause the video while you think about it. Dun, 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 dun. Okay, video was paused, you thought it over. And the reason for this is because we have a positive test charge. So if we put a test charge at this position right here, it will be attracted to our negatively charged object in exactly the same direction as our field arrow, right? How convenient. And if we put a positively charged object here next to our positively charged object, it will be repulsed in the direction shown by this arrow here. Okay, so there you go. So our positively charged objects produce a positive repulsive force, and our negatively charged objects produce a negative and attractive force on our test charge, preferably a proton. Okay. Next, we've got electric field strength, and you can find this in the data booklet, and it states that electric field strength is equal to force divided by our charge. Note that electric fields are a vector, So you could put a little arrow above here if you wanted to, and sometimes you see it denoted that way. The reason why it's a vector is because force is also a vector, little arrow here. And the force vector is divided by a scalar. So charge in this instance is a scalar quantity. So vector, vector, scalar. Okay, so based on this formula, you should be able to predict the unit for electric field strength. And I'm not going to pause the video because it's pretty straightforward. We know the unit for force, it's the Newton. We know the unit for charge, it's the Coulomb. So we've done our job. And our unit then, of course, is a Newton per Coulomb, or a Newton times a Coulomb raised to the negative first power. Okay, so if you plug Coulomb's law into this equation, go ahead and work out what happens. It would be worth taking a little time to work it out on paper if you want to. Obviously, I'm going to show you the answer in a second, but go ahead and do that if you're interested. Doon, doon, doon. More Jeopardy theme music. Doon, 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 doon. Okay, that's enough. So you paused the video and you whipped out a little piece of paper and you started doing some algebra. I've skipped a step or two here. Don't get too worked up about it. If you do it carefully, what you're going to find is that your test charge cancels out. And you're also going to find that electric field strength is equal to Coulomb's constant times the charge of the object that you are trying to measure the field around. And you will divide, of course, by distance from that object squared. So again, just carefully defining our variables. There you go. All variables defined. Nice. Okay, so again, our test charge cancels out, and therefore we only need to consider distance and the charge of the charged object, which is cool. And this is a big time saver. So also you will see this kind of stuff when you do topic 6. Some similarities are present here. This is super useful, and it's worth making a note because you don't want to have to derive it every time from the data booklet equations. So this might be one of those things you just put on a flashcard or something and stick in your head for later. It's really, really useful. Okay, next up we have metallic bonding and our charge carriers, which, as I already spoiler alerted you, is in fact the electron. Okay, so here we have a representation of a metal and metallic bonding, and the metal in question is zinc here. Zinc is a good conductor, as most metals are. In fact, all metals are. And the reason why they are good conductors is because they have these free or delocalized electrons that are capable of moving through the structure. Another good conductor would be graphite, which similarly has delocalized electrons that can move through the structure. Okay, normally, in the absence of an electric field, the movement of these electrons is random. Okay, so you could imagine this electron moving this way. Imagine a little arrow there for velocity, and this one might be moving this way. They're all moving in all different directions. So just kind of flowing around the positively charged ions, which are attracted to them. Oops, I've got a little animation problem here. Electrons are not the only possible charge carriers, but we focus on them in physics. Other examples would be ions, which are charged molecules or atoms. You'll see them more in chemistry in ionic solutions or molten ionic substances. In physics, though, we mainly deal with solid, at least in IB physics, we mainly deal with solids, and electrons are the charge carriers. Okay, so how do we get current then? Easy. We apply an electric field to the conductor, and that causes the electrons to move uniformly in the same direction, and they move opposite to the electric field direction. Okay, We'll look at that a little bit more later because it's kind of an important point. So here's electric current. Electric current is just the movement of electrons through a conductor. This is probably not a surprise to anyone. Direct current is the movement of electrons in one direction. I used to make a joke about a boy band, I believe, called One Direction, but I've stopped because I know nothing about them and avoid learning anything. We'll look at alternating current in topic 11. For topic 5, we don't really need to. So we focus on direct current, movement in one direction. Insert joke. Okay, so here we have a diagram and a formula. Nice. This is in your data booklet. Electric current, I, is equal to change in charge divided by change in time. Okay, so delta Q is the total amount of charge flowing through a given area of the conductor. So you just pick a spot in your wire or other conductive substance, and then you measure the amount of charge going through there in a certain amount of time. And that will give you your charge, okay? And this formula is going to be quite useful. However, we should also recognize that charge is quantized. And that brings us to our next formula. Okay? So, in a certain amount of time, a certain number of electrons, let's say this amount of time, a certain number of electrons is going to flow through that cross-sectional area. 1, 2, 3, 4, 5, 6, 7, 8. So in this case, we have 8 electrons flowing through this area in a certain amount of time. These electrons aren't going to make it through in that amount of time. So we can multiply the number of electrons by the fundamental charge, and that's going to produce a new equation for current where I is equal to N, the number of electrons, times the cross-sectional area, times the velocity of our electrons, times the fundamental charge, Q. And in this case, we are considering the average velocity of our electrons. And again, defining our variables. The average velocity here is what we call the drift speed of the charge carrier, okay? So this is how quickly the electrons are moving, and this is a net velocity, okay? So there's still some random movement of electrons, but they will have a single kind of net velocity, which is the sum of all of their velocities. Okay, Q is the charge of the charge carriers, and again, our charge carriers are electrons, so Q most of the time is going to be the fundamental charge. Done. I've already made this point, but when you actually calculate drift speed, and you will be doing this a little bit later, you're going to find that it's shockingly slow. And when I give you a handout, you'll consider that further. So I don't want to give everything away right now, but there's a reason why this very slow speed, despite this very slow speed, when you flick on a switch, the lights come on almost immediately. But this speed is very, very slow. You'll see. Okay, so now we're going to look at electric potential difference. And this is the amount of work per charge required to move a particle, in this case a particle of charge Q, through an electric field. So from the data booklet, we have electric potential difference, V, given as work per charge, just as we set up here. How convenient. Our unit for potential difference is energy per charge, and this is a volt, which is named for Alessandro Volta, who died in 1827. he invented the electric battery, and I have a Leyden jar in my lab that probably looks not too dissimilar from some of the early batteries that Volta was playing with, although I'd have to check into that. He may have been doing electrochemical batteries, which a Leyden jar still technically is. But anyway, let's move on. So here we have 1 volt equal to 1 joule per 1 coulomb. And so there's our unit. So another quick point, our energy involved here could be either potential or kinetic energy. So keep that in mind when you're working problems. Okay, finally, and we're kind of wrapping up our lecture here, we're going to deal with electron volts. So an electron has a charge, so if we move it through an electric field, it's going to experience a force. As we know, work is equal to force times distance. So if we move this electron through an electric field, that's going to require work, okay, by definition. So the amount of work required to move an electron through a potential difference of 1 volt is called an electron volt. And here is the math. So we rearrange our prior formula for volts such that work done is equal to charge times voltage. Conveniently, we've set voltage to 1 volt, and we know the charge of an electron, it is 1.60 times 10 to the negative 19 coulombs. So we just have to multiply this by 1. So simple, so easy. Our coulombs cancel out, because remember a volt is equal to a joule divided by a coulomb. So these coulombs cancel out, and we're left with 1.6 times 10 to the negative 19 joules per electron volt. Wow, so convenient. This is exactly the same magnitude as our fundamental charge. Very, very useless. Useful, not useless. Okay, so this is going to be in your data booklet, and we're going to see it again, particularly in topics 7 and 12, because it's really, really useful. When we're dealing with very small amounts of energy, it's a lot easier to use a few hundred electron volts than 1.6 times 10 to the negative 16 or whatever. So if you can avoid scientific notation, you should. Okay, so you need to be able to convert energy into electron volts and vice versa, and it's quite an easy conversion. Here's the conversion factor. Don't sweat it. So there you go, everyone. Here are my sources if you're interested in, and I use Google Slides, LaTeX, and Adobe Illustrator. Do not click like, do not subscribe, but do have a fantastic, fantastic day.